So I would say that we can go for the next talk. So the next talk is Samaya Nissanke from GW+, and she will talk about new perspectives onto the universe in the era of multi-messenger astrophysics. Thank you.
Can you hear me okay?
Yes, we can hear you fine.
Okay. Great, thank you. So good afternoon. So firstly, I'd really like to thank the organizers for inviting me to talk about this rapidly exploding and now observationally driven field of gravitational wave and multi-messenger astrophysics, where we're essentially seeing these multiple fields, general relativity and gravitational waves, computational and statistical astrophysics, transient astronomy, cosmology, all converge to allow us to make this tremendous advance that we're seeing now in strong field gravity astrophysics. And so I'll be talking about work and results that have been done in large and gravitational wave and smaller electromagnetic collaborations, as well as work done by members of my group. And without further ado, of course, it's very important to stress that this transformation that we saw 5 years ago with the first discovery of a binary black hole merger by the LIGO and Virgo collaboration was really only made possible by the incredible instrumentation and engineering advances of ground-based gravitational wave detectors, work that took several decades and hundreds of individuals. And so during the first science run, the two LIGO detectors measured these 3 binary black hole mergers, resulting in the first direct detection of gravitational waves, the pairs of black holes merging. And shown here is a schema where the vertical axis denotes the masses in solar masses. The horizontal axis doesn't have any significance, and the blue bubbles represent the progenitor and the final black holes that were observed in gravitational waves. And shown by the purple as well as the yellow bubbles are the black hole and neutron stars that were previously inferred from X-ray and radio measurements. Now, I remind you that this first event, GW150914, dubbed by the dates of the observation, released 3 solar masses of energy in 0.2 seconds, making it the most luminous event that we'd ever observed in the universe. Now, since then, thanks to instrumental upgrades that during the second science run in 2017, we saw the European-based Virgo detector come online and the discovery of a further 7 new binary black hole mergers and the game-changing GW170817, our first binary neutron star merger that was seen in both gravitational waves and in every part of the electromagnetic spectrum. And this electromagnetic emission essentially arises from the delayed matter outflows that are happening as the merger of 2 compact objects occurs, where at least one of the objects is anticipated to have matter. And this remarkable discovery led to several firsts, including the first time we could actually pinpoint a gravitational wave event in the sky, the first discovery of a kilonova and the sites of astrophysical R-process elements, the first association of a short gamma ray burst with a neutron star binary merger, the first Hubble constant constraint, as well as the first constraints of the speed of light and gravity. Now, moreover, in 2019, thanks to further instrumental upgrades, increasing the detector sensitivity by a factor of 1.5, during the first half of this third science run, referred to as O3A, we have now observed at least 50 compact object mergers. And of course, in June this year, we announced the discovery of the first 2 neutron star black hole mergers seen in gravitational waves with masses 9 and 1.9 solar masses and 5.7 and 1.5 solar masses, which arose from the second half of the third science run. Now, there are several things I'd really like to stress. Number one, we're really uncovering a diversity of the fundamental properties of black holes, as well as neutron stars, and folding in selection effects. These indicate a broad distribution in the masses, with some systems showing some asymmetry. Several open questions remain as to the nature of the remnant, in particular for these binary neutron star mergers, where we're observing black holes being formed in essence in real time, and as to hypothesized mass gaps that were thought to exist between sort of the maximum mass of neutron stars and the lowest possible astrophysically produced black holes. And so we're able to now actually test this and probe this regime. And there are several independent analyses using the open data of the LIGO, Virgo, KAGRA collaborations, which are revealing other interesting candidates. Now, for the rest of this talk, I'm going to focus on several characters, GW170817, GW190425. This was the second binary neutron star merger that was observed with a total mass of 3.4 solar masses with no electromagnetic counterpart seen and a much weaker signal to noise ratio. GW190814, the most asymmetric mass binary with the smallest localization that we've seen so far in 2019, and the first alerts actually suggesting it was a neutron star black hole, as well as these two neutron star black hole events that were announced this June. So those are the characters I will be focusing. And what I'd really like to stress is, of course, this gravitational wave and multi-messenger measurements are really impacting a diverse set of different fields. And so due to the limitations in this talk, I really should add a disclaimer that I'll only be talking about certain aspects and really trying to highlight the perspectives as I see them, a very personal view in terms of the future of multi-messenger astronomy in the near and longer term, but really just to stress the bigger picture, as well as the fact that there have been thousands of incredibly interesting papers written about this one event in the last few years. And so taking a step back, our measurable in gravitational wave astronomy is this dimensionless gravitational wave strain, h of t, which has this important 1 over the distance to the source dependence. This essentially allows these to use them as absolutely calibrated distance measures, for instance, in terms of cosmology. And they have these two polarizations, H plus and H cross, which are essentially being measured by these current interferometers, which are essentially measuring a linear combination of the two polarizations, H plus and H cross, which are weighted by the detector antenna function. And during the frequency band of these detectors, the most numerous source that we are seeing are these compact object mergers, neutron star black hole mergers. Now, in order to actually pull out information, we really rely on accurate source models of what this dimensionless gravitational wave strain looks like. And so this is the so-called gravitational waveform, which comprises these 3 phases, the so-called in spiral, the merger, as well as the ring down. And so the in spiral is modeled extremely accurately using the post-Newtonian approximation. It's driven by the so-called chirp mass, a combination of the 2 masses that appears at Newtonian order in the phase as well as in the amplitude of the signal. And parameters such as the reduced mass, the spin orbit, the spin-spin coupling, as well as the tidal deformability containing any information about the internal structure of the object appears at increasingly higher order in the phase of the waveform and can cause significant beating and modulation of the waveform, especially for asymmetric systems, really impacting how well we can actually retrieve the source parameters. The merger requires numerical relativity, really solving Einstein's field equations in these dynamical, strongly curved spacetimes. For instance, Luciano, our previous speaker, is an expert of this area, as well as the post-merger really describes the settling down of the final remnant of the merger. Now, it's important to stress that the detector sensitivity is more sensitive to a particular epoch of the waveform that depends in turns on the different masses. So for tens of solar masses, binary black holes, we're essentially observing only tens of the cycle of the merger phase, lasting a fraction of a second. Now, for these lower mass systems, these neutron star, neutron star, neutron star black hole systems, we are observing thousands of the orbits of the in spiral in the frequency band of these detectors. And currently, the post-merger signatures are outside the current sensitivity band at a few kilohertz. And one immediate task for the community is building these gravitational waveforms, really inputting more and more physics into these, as well as building waveforms for theories beyond general relativity in order to actually test general relativity. Now, with these waveforms in hand, one can then actually cross-correlate our detector signal with template banks of our model 10 to the 5, 10 to the 6, and not only for detection, but then to actually extract the source parameters, source information. So we're explicitly mapping out these posterior probability density functions using MCMC, Markov chain Monte Carlo, nested sampling, as well as now machine learning neural networks, convolution neural network techniques are now coming into play. And it's important to stress here that these are really the parameters that we can infer currently from the gravitational wave strain. The redshifted masses, the spins, the tidal deformability appearing really in the, impacting really the phase of the gravitational wave, and geometric properties such as the inclination angle, source position, and luminosity distance, which appear in the amplitude of the phase where there are much stronger degeneracies. And so how well we can measure these parameters that appear in the phase really depends on the length of the signal, which part of the waveform is in the sensitivity bucket of the detector, which in turn actually depends on the masses of the system. And typically the full analysis can take a day to several weeks, depending on the dimensionality and the complexity of the waveform. And of course, for electromagnetic follow-up, we wish to speed this up to the minutes time scale. And so this is really the next big task, is really the faster and analysis for more accurate and more precise measurements. So as an example, what I'm going to show here are the 2D PDFs for the masses of the heavier object and the lighter object in the case of GW170817, where this narrow banana really sweeps out this line of constant chirp mass that we were able to measure to 1 part in 1,000, and the other directions is determined by the reduced mass, which appears at the higher post-Newtonian order. And the red and blue contours essentially show the dimensionless, if one assumes a dimensionless spin magnitude in the direction perpendicular to the orbital plane of 0.89 and 0.05 respectively, what I really want to highlight is this really shows the degeneracy between the mass ratio and the spins in the in-spiral. Now, really, it was this plot that indicated that first event was a binary neutron star, really the consistency of the masses with the known galactic binary pulsar distribution, in addition to the fact that we observed a kilonova, so knew that at least one neutron star was there in the system. But really, these mass measurements were critical. Now, if we turn to GW190425 with a much weaker signal to noise ratio of 12.9, the banana is much thicker, as you can see, and relaxing the spin assumption, the mass of the heavy object ranges from 1.12 to 2.52 solar masses, really begging the question, was this heavier object a neutron star or indeed a black hole? And I'll return to this question and ask whether electromagnetic observations in the future may help for this particular system. And in the case of GW190814, due to the masses of the system, this very asymmetric binary, the 2D PDFs are much less banana-like. We're much less sensitive to the chirp-driven in-spiral, so we don't have that nice chirp-like contour. And the heavier mass here was 23 solar masses, and the lighter object being about 2.5 to 2.67 solar masses. Really a central question here was whether this was the lightest black hole we had seen, or indeed the heaviest neutron star we'd ever seen. So in the interest of time, I can discuss these in the discussion section, but I'll move on now to the actual multi-messenger aspect and the fact that if we want to talk about doing follow-up, how well gravitational waves alone can localize the source is really critical. Indeed, these interferometers have these very quadrupolar antenna functions, really poor angular resolution, and we really rely on the triangulation or the time of the arrivals of the signal of our different detectors in our worldwide network, as well as some information of the quadrupolar antenna function. So for this GW170817, we were able to actually constrain this event to 30 square degrees, and with a distance of 40 plus or minus 10 megaparsecs. And I'm going to return to this and give you some idea about how subsequent events have compared to this one event, so in terms of the numbers. Now, with these with the sky error, as well as the distance measure from gravitational waves, what observers were able to do was actually to basically cross-correlate this, or look at basically how many galaxies were in this gravitational wave volume. And by targeting the brightest or else the most luminous galaxy actually resulted in the optical transient being detected in NGC 4993 at 10.8 hours after the event. The first alerts were sent at 5 and 10 hours after the event, and the actual event was seen by the SWOPE telescope in Las Campanas in Chile at 10.8 hours. This bright blue flash denoted by this red arrow. And you can see in the archival image, this transient did not exist. And so what was really incredible was that this first flash, in some sense, optical flash, ended up being the real deal, but it required sort of subsequent photometric and spectroscopic observations over the next days to weeks, really indicating that this transient was very unlike any event that we'd ever observed before. And what we are now seeing for gravitational wave triggers with much weaker signals, that there are many, many other transients and variables in these large patches of the sky. And indeed, we have to face this needle in the haystack problem of actually identifying potentially the kilonova or neutron star optical counterpart of these neutron star black hole mergers. So you can ask the question, well, did we just get lucky with that one event? Why have we not detected other electromagnetic counterparts? Well, let's just consider what happened in the public alert era of 2019, where the LIGO, Virgo, KAGRA collaborations were sending out alerts to the entire world. And so there were 56 non-retracted alerts sent out. 8 were for binary neutron star and 7 for neutron star black hole systems. From their initial classification, many actually changed in the subsequent time afterwards. And the median localization for these events was 4,480 square degrees. So large, essentially, because several of these included were only detected by one detector, because the other detectors were offline, either for repairs or just not running at the same time. And the distances were about 230 to 350 megaparsecs for neutron star black hole systems. So in the case of GW190425, this binary neutron star merger that was classified immediately, the gravitational wave sky area was actually a quarter of the sky. Okay, it was 300 times larger than that of GW170817. But really impressively, there are new facilities coming online, such as the Zwicky Transient Facility with a field of view of 47.5 square degrees that was able to actually tile the northern hemisphere part of the initial sky map to about 40%. Okay, so really, I was quite amazed that this was even possible to do this within the subsequent couple of days. Now, in the case of GW190814, this had a much smaller localization of only 18.5 square degrees. But in this case, the challenge was really the depth. It was essentially seen at 240 megaparsecs. And this distance is essentially 6 times that of GW170817, our first multi-messenger discovery. So really, many telescopes were able to actually point very deeply by stacking images to really try to hunt in this area. But indeed, what ended up being the case was that the neutron star, the black hole, was so heavy in this system. If you remember, I said it was 23 solar masses, I think. It essentially swallowed the neutron star merger whole without there being any matter outflows and resulting in an electromagnetic counterpart. So to really just to stress, these are the challenges: the depth, the sky coverage, as well as what is the information of the masses of the system, really impacting how follow-up is proceeding. Now, if we move back to GW170817, what made this, I think, such a celebration was the sheer amount of data that was obtained by over 100 instruments. Over 3,000 people were involved in the initial discovery paper. Shown here is the flux density as a function of the time after merger. And what I really like to stress is the necessity of having different measurements in different wave bands is key to actually probing the physics that is driving the merger and the post-merger evolution of the systems. Okay, and you can really see in this figure that there were two classes of observations or data, those relating to the ultraviolet, optical, and infrared, as well as those relating to the radio and X-ray observations. And so I'll come to what we were able to say, or the sort of highlights that we were able to say from these observations. But what I think made it very at least for me, so spectacular was that at zeroth order, they really agreed with the prediction that there should be at least two types of electromagnetic counterparts associated with neutron star, neutron star, neutron star black hole systems. The first is the kilonova, this rapid neutron capture nucleosynthesis powered transient that emits thermally in the UVOIR, essentially lasting days to weeks. And this is coming from either the tidal tails or short-lived accretion disk winds, or else indeed from the two neutron star systems actually smashing into each other. And the second counterpart is the short gamma ray burst, hypothesized for decades to be coming from these systems, where essentially you have accretion onto a centrifugally supported jet disk, which is powering this relativistic jet. Okay, that slams essentially into the circummerged environment, and this jet decelerates, producing synchrotron radiation, which is then observable in the radio and the X-ray, as we've seen. And here the emission very much depends on the line of sight of the observer to the barrel of the jet. And so, therefore, from the electromagnetic counterparts, what we're learning and inferring is a whole host of orthogonal and complementary information, not only the redshift, but information about our process nucleosynthesis, with the mass eject and the velocity, as well as the environment. I'm showing here a beautiful movie of snapshots from ESO's Very Large Telescope that were taken in the subsequent 10 to 14 days after the event. This is real spectra that you're seeing of this event, but really demonstrating to us that we were seeing for the first time this one of the astrophysical sites of our process elements, as you see from these broad line absorption features of these heavier elements at the bottom of the periodic table. And so one huge task now facing the community is really modeling the outflow microphysics, being able to actually relate your electromagnetic observables with actually the microphysics that is happening in the post-merger. And another sort of highlight result I'd like to stress, which has important implications for cosmology, for instance, are the observations that were seen by the Very Long Baseline Interferometry, really in the spirit of the talk we just heard, the beautiful talk we just heard, which occurred actually in the year subsequent to the actual merger, where two different epochs of observations really were able to constrain the proper motion of the centroid of the source, resulting us to actually infer the inclination angle to the binary to 20 plus or minus 5 degrees, really impacting how well we could measure the distance to the source from gravitational waves alone, and using these systems as standard sirens, essentially distance ladders. So really this combination of gravitational wave and electromagnetic observations. Now, there are many open questions remaining from these events that we haven't been able to answer, that many groups are working on. What is actually producing this jet, the central engine, really kind of fundamental questions in astrophysics, as well as things like what is the role of the jet disk interaction? Do we need to form a black hole promptly to actually launch the jet? So really, Many questions still open for future events that we aim to study, but really brings me to this new field that is really active, where we are combining these different data sets, gravitational wave and electromagnetic observations. And one of the big challenges here is, of course, the large number of parameters, the yet to be identified degeneracies here, as well as, of course, the modeling uncertainty and really being able to model the electromagnetic light curves of these systems. And to do this, both for the strong signal binary that we've already seen, but to really start to do this joint multi-messenger effort for population of events. And so I'm going to return to, as an example of sort of this joint gravitational wave and electromagnetic effort that we're making, I'm going to return to this question of how gravitational wave and electromagnetic measurements may have helped in actually saying something about the progenitor of this GW, of this second binary neutron star that we did not see an electromagnetic counterpart. But the question we posed, and my PhD student at the University of Amsterdam, Hert Rijmakers, posed and really built a beautiful end-to-end simulation, end-to-end toolkit, which will be going open source, hopefully at the end of this year, allows one to make these kind of answer these kind of questions. So what we're showing here on the left is a suite of model light curves from different groups all over the world. And then what we did on the right was actually looked at a variety of cases where we could assume whether the electromagnetic modeling uncertainties were improved, as well as the photometric measurements for this particular low signal to noise ratio binary. So what you can see essentially on the right, shown in gray and shown in red, are the 2D PDFs for the mass ratio, the tidal deformability, and the black hole spin for this, in some sense, very typical kind of low threshold kind of event, and the improvement that we may be able to make in terms of defining the actual nature, as well as fundamental properties on things like the tidal deformability. Now, a critical ingredient for this analysis, as well as for electromagnetic follow-up, are the semi-analytical formulae that are relating the progenitor properties to the initial outflow properties. And in the case for neutron star black holes, the central question is whether the neutron star is swallowed whole by the black hole. And in this case, in the case for neutron star black holes, we essentially calibrated, Francois Foucault, calibrated essentially these formulae with 75 numerical relativity simulations. And as you can see in this phase space plot of the black hole spin here, on the vertical axis, the tidal deformability, on the horizontal axis for different mass ratios, the color bar here shows essentially how much matter is predicted to be released from numerical simulations. And you can essentially see that there's only a certain sweet spot in the phase space for essentially high black hole spins, low mass ratios, and relatively stiffer equations of state of the neutron star, the compactness or the fluffiness of it, that it allows for matter outflow. So really the bottom line being is that for neutron star black hole systems, we only expect a small fraction to actually be associated with electromagnetic emission. Now, in the last 5 minutes of my talk, I'd just like to end with sort of the immediate perspectives of the immediate challenges I see them going forward to actually witnessing black holes being born for the first time from neutron star, black hole systems. Number one, to really stress the importance that we expect a diversity of electromagnetic counterparts from these systems, which really depend on the total binary mass, the remnant, whether it's a longly lived or stable supermassive neutron star, or a metastable hypermassive neutron star, indeed promptly collapsing to a black hole, as well as the mass ratio. This will really determine, as we are seeing both from theory as well as our one event, what the electromagnetic counterparts we can expect to look for. The second is a challenge really the computational astrophysics side of the aspect is really, in order to do this joint gravitational wave and electromagnetic combination, is to build this coherent model of the binary evolution, the merger dynamics, and the radiation transport to be able to join these different sets of observations, where of course the big challenge is the huge range that we need in both distance as well as time scales to do this. The third challenge to stress is that there are lots of aspects of the electromagnetic counterpart emission that we don't necessarily understand, which really impact how well we can do this joint GW+EM in terms of the fundamental properties. One of the things for GW170817 was we missed vital ultraviolet and optical information in the first 10-11 hours, really saying something about the emission mechanism. And indeed, there are several UV missions currently under design and proposal, which are aiming to really go after this ultraviolet emission from these neutron star, black hole neutron star mergers. The fourth challenge is that we have really moved from individual objects to statistics, as highlighted by this cumulative number of events count in the first 3 science run. Note that from aside from the 2 neutron star black holes that we announced, we have not yet released the O3b catalog. And so but this really gives you an indication of just the sheer number of events that we have to be prepared not only to analyze, but of course to understand how to interpret really in their true astrophysical and cosmological context. And so in the next coming years, when the 04 run for LIGO, Virgo and KAGRA come online, we can expect tens of these systems per year, and neutron star black holes also similarly tens, but just with this caution that only a fraction of these are expected to have electromagnetic counterparts because of this very sweet spot that allows for there to be matter outflows. In 2022, fortunately, we will have new instruments such as LSST in the Vera Rubin Observatory, as well as really the SKA precursors in the radio coming online, as well as other astroparticle experiments really also able to probe these kind of mergers. And of course, in the 25-27 era, LIGO India will be coming online, really shrinking those errors and making, in some sense, electromagnetic follow-up much more doable, as well as, but having to deal with perhaps events happening further out. And then, of course, I think what is particularly exciting especially for the early career scientists in the audience is the prospect of 3rd generation gravitational wave detectors in the mid 2030s or late 2030s coming online, the Einstein telescope in Europe, as well as the Cosmic Explorer led by the US, where the target sensitivity of these instruments is a factor of 10 greater than the projected design sensitivity of advanced LIGO in 2023. And so we're talking about a factor of 1,000 in terms of the sheer number, or in terms of the rate or the sheer number of events that we'll be able to see. So what I'm showing here, and this is something I think is just spectacular in terms of the way we have to transform the way we are, I think, thinking of observational measurements of black holes in particular, as well as neutron stars, is the sheer number of events we may be talking about having to analyze and really use. So shown here is the redshift as a function of the total source mass. In green here is the horizon distance for the Einstein telescope. In pink here is the horizon distance for Cosmic Explorer. And so what I really want to stress is the redshift range that we'll be able to see for these objects of this total source mass. GW170817 is off the plot at the bottom, as a redshift of 10 to the -2 or so. And really in this case, we're expecting 10 to the 4 to 10 to the 5 mergers, neutron star, black hole mergers happening per year. Okay, so we'll really be seeing every observable event happening, merger happening. And of course, this requires this radical transformation in the way we're thinking of multi-messenger astronomy, not just to think about following up individual events, but really also to maximize the sheer number of events that will be way too far. For instance, here in this case, we even our most sensitive optical telescopes such as the ELT will only be able to go out to a redshift of 0.5 or so. And so really, the vast majority will not have light curves that will be detectable by even our most advanced optical and radio facilities. And so really to maximize the sheer number of gravitational wave events, really to use these as probes of large scale structure and extragalactic astronomy. And so that is happening right now today. And of course, I'd just like to end with a reminder that I have really focused only on the high frequency end of the gravitational wave spectrum that spans decades of frequency space. But of course, there are many experiments that are already ongoing, as well as future experiments such as LISA that will be targeting gravitational wave sources in different masses with different masses, and indeed which should have electromagnetic counterparts as well. And so really just to stress that the future is both loud and bright. So thank you very much. I hope I'm within time.
Yes, roughly, yes. Thanks,
Okay.
Samaya.
Thank you.
Great. We have time for a couple of questions, probably. So I see one. I don't know how to give that because I see anonymous attendee. So I have to see if I can spot it.
Yeah, I can see the question. So the question was, the first slide had yeah.
Exactly. The first slide had an electromagnetic black hole in it. Does that mean that binary black hole mergers do have an electromagnetic counterpart as well? If yes, what causes it?
Thank you very much for that question. So the first slide, which was really that bubble plot where there are electromagnetic black holes, those are seen from X-ray binaries, essentially. So where you have a main sequence star, which is being accreted onto from a black hole. And these were our previous measurements, essentially, of black holes. So they were inferred by, observing essentially how the accretion of a companion star was they were very model dependent measurements, but similar to what Luciano was talking, was really dependent on the accretion physics that you were having to model for inferring actually the black hole mass. And so those were for the first slide. But to your second part of the question is, it's gone. But the second part was, do we expect electromagnetic counterparts for binary black holes? Well, yes. So certainly in the case of supermassive binary black holes, we do expect them to be embedded in very heavy matter environments. For instance, where we know that there are AGN disks, etc. So in the case of supermassive black holes, it's very much accepted that there will be electromagnetic counterparts, and something that the LISA telescope or LISA interferometer is really going to be combining with multi-wavelength observations. In the case of stellar mass binary black holes, it was originally thought that most of these systems do not have enough kind of plasma or matter around them to be detectable, but actually there have been several interesting models being proposed. For instance, if you have a binary black hole merger that occurs, for instance, in an AGN disk, this may indeed cause some kind of transient signal as you have the black hole essentially recoiling through the disk. And so there have been proposed models, and indeed there has been at least one candidate for GW190521, the first intermediate mass black hole that LIGO and Virgo and KAGRA saw, where there was a tentative candidate by the Zwicky transient facility that was seen that could possibly agree with this hypothetical model. So really just to wrap up the kind of my summary, I think that given the sheer number of binary black holes that we're seeing, it is within reason that at least a small percentage of them may have electromagnetic counterparts. Yes, and depending on the formation channel or the environments where these are from. Thank you.
Okay, great. I think that there are another couple of questions, but it seems to me that they are good questions for the discussion. So I would keep them for the discussion and move on to the next speaker.